Examination Program 2023 will be conducted by mentor of the mentors, great mathematician, and he is Shri Prasad Tambe sir. Let me take this opportunity to introduce Shri Prasad Tambe sir. He has done MSc Maths from IIT Bombay in 1992 with NBHM scholarship. He has also done research in algebraic number theory. He is working as a trainer for Maths Olympiad at national level. He is giving coaching for MSc and PhD entrance tests. He is also a resource person for Madhav Mathematics competition at UG level, undergraduate level. He has given lectures on number theory, cryptography, IIT Jam in various colleges, author of docudrama on mathematics for Akashwani, member of writers team of Kutuhal column on mathematics in Lok Satta, Marathi newspaper Lok Satta in the year 2021. He has been giving guidance to the schools in setting up math lab, and he has personal collection of about 10,000 books on various subjects. About 10,000 books. Give him a big round of applause. He is running the activity like Math Circle for NGOs, RAM foundations, and he has experience of 30 years in teaching field. So let us again welcome our eminent resource person.
More important, level of a great human being. Because I can share the experiences with you all that when I interacted with Sir to be the resource person of this program, despite being so busy and Sir is teaching high level students also, and Sir has to travel more than 1 hour and to come to us to interact with us. Sir readily agreed for our request and came here and also assured us that in future also whenever we need, he will surely guide us. So this, these all things are worth learning for all of us. That despite having so much vast experience and Sir has produced many Olympiad qualifiers, despite that, Sir is ready to help and is still so much humble and down to earth. I welcome you, Sir, once again on behalf of all of us, and it's really our privilege to have you here. Thank you so much.
So thank you for inviting me and for giving the opportunity to interact with the entire. Have you got this sheet? Problem sheet? Okay. Yeah. So I'll be talking about number 8 as we must be doing. There are mainly 4 topics for Olympiads: algebra, geometry, combinatorics, which we are in the morning, and number theory. So I'll be talking about number theory. Yeah, anyway, it's no problem. No problem. So I guess this is course number 3 session, and I'd like to give some references. So if you want to start with number theory, in particular number theory, not for Olympiad, a good book to start with is by David Burton. So elementary number theory, by David Burton. Another book through which I learned in my BSc mathematics course Introduction to the theory of numbers. Introduction to the theory of numbers. By Eugene Zuckerman. It's a classic book for many years. Now I did my BSc in 1989, so that time it was a well-known book by Zuckerman. And the fifth edition is revised by Montgomery, the student. So particularly Newman was the head coach for US and mass arithmetic, and therefore there are many nice problems in this book which are typically Olympiad type. Yeah, so that's for elementary number theory. And if you want typically Olympiad style books, so I say Olympiad number theory. There is a nice book. In fact, all these are available online free. So there is a nice book, number theory by Aditya Kurmi. I hope some of you must be knowing it. Aditya Kurmi. And nice part about it is he is himself Olympiad student, and I hope he went up to IMOTC. And when he was in 12th, he had written this book. So now I think he is learning somewhere abroad. So it's a very nice book and very recent book. Another classic book is 104 number theory problems by, again, if you are familiar with Olympiads, you must be knowing this name, K2 and Rescue, and some others. Yeah. So these are mentioned in that problem set. Another book by, which is typically Olympiad type, number theory by Amit Parvati. This is typical Olympiad type book. Yeah, but for Olympiad, generally we come across only problems. But if you want to solve problems nicely, in fact, you should be very good at basics and theory, and therefore you should learn some standard results from these books. Can I use this? Yes, I have two sections, and in both sections we have some simple and basic problems from number theory, and I try to show the connection with some theory part of number theory. And in second lecture, we do some little advanced prediction of problems. Yeah. Yeah. So the first one. Uh, what is the question? Find primes P and Q such that P square minus 2Q square is equal to 1. Yeah. So as I said, try to show every time connection between some very part of number 3 and the problem. So this is typically problem of the form x square minus dy square equal to 1. What is the equation called as? It is called as Bell's equation, or it was studied in India much before Bell as Brahmagupta, or as Brahmagupta field equation. And there is a nice theory of how to solve such Bell's equation. We'll see some part. Yeah, but in this case, in addition, what we have is those numbers are primes, right? What are prime numbers? Yeah. So those positive integers which have exactly two divisors, one and itself, right? So obviously one is not a prime number. One is neither a composite number. So what are prime numbers? 2, 3, 5, 7, and so on, and so on. Right? In fact, in Olympiads, one should know the year in which you are studying. So what is the factorization of that number? So for example, possibly you will be giving exams in 2024. So let's try to find prime factorization of 2024. Can somebody quickly find prime factorization of 2024?
8 into 11.
Yeah, 8,
11,
11,
11 into 20.
That 20.
20. Yeah, so this we can write as 2 raised to 3 into 11 raised to 1 into 23 raised to 1. Fine. So that fraction also tells us many things. For example, say number of divisors, sum of divisors, etc. So that's 2024. Okay. So how do we solve p square minus 2q square equal to 1? So for example, 2q square, I can take this side and I take 1 this side. And there's some nice algebraic expression p square minus 1. Right? If you can simplify further, so what is p square minus 1? P number theory problems. A square minus b square is 8. And we see some typical problems which use this identity. Yeah, so 2q square is p plus 1 into p minus 1. What can we say now?
So P plus 1 and P minus 1 have GCD 2. Or either they have GCD 2 or they are both.
Right. So either 2 or 1. Right? Yeah, so one talks about essentially parity in number theory, and when it comes to terms. So what is parity when the number is even or odd? Right? So for example, this I have 2q square. Right? 2q square. So which means what? LHS is even number. Right? LHS is even. So what can I say about these numbers? So both cannot be odd. Both can't be odd. Right? So say for example, at least one of them is even. Let's say suppose this is even, but as he mentioned, in fact, difference turns out to be 2. So if this is even, this is also even. All agree? Right? Yeah. So now there are two even numbers, so this side is divisible at least by 4. At least by 4. Is that okay? Yeah. So q square is p plus 1, say by 2, I am taking 2 this side, into p minus 1, and this is surely integer. So integer times some even number, right? So very good. Integer times some even number. So q square is even integer. Now if q square is even, what can we say about q? Q is also even. So very good. And I know q is prime. So what can we say about q? Yeah, so q is Why? Because it's even prime and only even prime is 2. So 2 onwards all primes are odd. Right? So Q is 2 and once Q is 2, once Q is 2, I can put insert that value there. So P square minus 8 is 1. So P square is 9. I know P is prime since greater than 1, so I take positive root. So P is 3. Fine. So solution is P equal to 3, Q equal to 2. Okay? Yeah. Yes. So Q square is even, right? So it's some integer because P plus 1 is even. So I divide by 2. After dividing by 2, it's even. It's not fraction. So some integer times even number, right? And which means Q square is even number. But Q square is even implies Q is even, and Q is prime number also. So only even prime is 2. So Q must be 2, right? Yeah. So there is one more nice problem from number 3 connected to this. As I said in first lecture, I am trying to show connection of these problems with some number 3 problems, some research in number 3. So I put those values here. So 3 square minus 2 times q is 2. So 2 times 2 square, which means 2q is equal to what? And there is a nice result in number 3 known as, so earlier it was known as Kaplan conjecture. Now it's proved it's not known for as conjecture. What is conjecture? Conjecture, some result which is not yet proved, which is, or there is nobody who has disproved it, or there is no proof for that. Right? Something which is neither proved nor disproved, that is conjecture. Okay, but this was recently proved. In fact, this case it was conjectured by Kaplan in 1844 in what is called a trade journal. Trade is the person who started that journal, and fortunately that journal is still into working. And in 2004, in same journal, trade journal, Prada analysis proved the result. I don't know how to pronounce that. Proved it in same journal. So proof also is accessible. You can also understand the proof. It uses little bit of algebraic number theory. Otherwise, you can also understand the proof. Yeah. So that's the story. And what's the statement? What are the conjecture? So Kaplan conjecture that if I consider Diophantine equation, what is Diophantine equation? Where we want to see integer solutions. A raised to x minus b raised to y equal to 1, where all those a, b, x, y are natural numbers. Naturals. And those powers are at least 2. At least 2. Right? Then only solution is 3 square minus 2q equal to, that's the only solution. Right? We know many equations where there are infinitely many solutions. Right? So for example, Pythagorean equation, say a square plus or x square plus y square equal to z square. And I know there are infinitely many solutions. Right? But here is a equation which has only one solution, namely 3 square minus 2q is 1. Right? But that was difficult to prove, and it took so many years to prove it, almost 160 years. Another such famous number 3 problem is Fermat's last theorem. Right? So it was conjectured around 1640, and it was proved in 1994. We'll see how many years it took to prove. Yeah, so this problem has connection with Kaplan equation, Kaplan conjecture. Find the first one. Shall we go ahead? The second one. Can I write written about this? Backside students, you can see this part. I have this. Yes, what is second one? Oh, by the way, that first problem was from junior RMO. Junior IMO conducted by Boston Shriprasad. I think year was from 2004. Don't remember exact year. Yeah, no problem. Okay, so second problem is from PIMO. In fact, few years back, instead of IOCM, there was something called as pre-regional mass Olympiad.